So, let x1, x2, xp be a discrete random variable with joint probability mass function fx, then x1, x2, xp are independent if and only if in the joint PMF you can separate out the terms of x1 and x2 and xp. So, which is equivalent to saying that in joint PMF can be written as product I is equal to 1 to p gi xi, x belonging to x1, x2, xp belonging to rp. So, this is equivalent to saying that you can separate out the terms of x1, separate out the terms of x2 and separate out the terms of xp throughout, and this happens for some non-negative functions gi. Now, if that is the case, you can check what would be your marginal PMF of xi. So, certainly marginal PMF of xi has to be, you integrate out the unwanted variables which would be x1, x2, xp minus 1. So, gi x would be left. When you integrate out rest of them, let me call that as ci. So, the probability mass function of xi would be ci gi x for some positive constant ci. And what would be the support of ci? Ci would be collection of all those x belonging to R such that gi x is positive, where this is positive. So, I give this the proof for p is equal to 2. So, I take p is equal to 2. First, suppose that x1 and x2 are independent, then I know that joint PMF is same as the product of marginals. Then certainly this 2 holds with the choice g1 x1 as fx1 x1 and g2 x2 as fx2 x2. So, if x1 and x2 are independent, then this clearly 2 clearly holds. Now, suppose 2 holds. So, suppose 2 holds. Then first I look at what is the support. Support is collection of all those x belonging to R2 such that fx x is positive, which is same as collection of all those x belonging to R2, because fx x is nothing but g1 x1, g2 x2 is positive, which is happens if and only if g1 x1 is positive and g2 x2 is positive. So, this is same as collection of all those x1 belonging to R, g1 x1 is positive multiplied by the second argument, which is collection of all those x2 belonging to R, g2 x2 is positive. So, it is a cross product of these two sets, which is same as S1 cross S2c. What is a marginal probability mass function? fx1 x1 is same as this. So, I have to show that x1 and x2 are independent. To show that, what I will do is I will show that joint probability mass function is product of marginals. So, first I try to find out what are the marginal distributions. So, fx1 x1 is this. So, to get this, I sum out the unwanted variables. Unwanted variable is x2 is equal to t. So, I sum out the t. So, this is a collection of all those t such that x1 t belongs to Sx. So, probability x1 is equal to x1, x2 is equal to t. I write down this as, this is same as union of singletons I have written down over here. So, this is same as summation t x1 t belongs to S1 cross S2, because Sx is same as S1 cross S2. G1 x1 G2 t. Since I am summing over t, G1 x1 comes outside. So, summation t belongs to S2 G2 t, and to ensure that I am not summing over an empty set, my x1 has to be in S1. If x1 is in S1, the only condition I need is t belongs to S2. So, that is what I am doing over here. And if x1 does not belong to S1, then I am summing over an empty set, and this would be 0. Similarly, if x2 x2 would be g2 x2 summation s belonging to S1 g1 s if x2 belongs to S2 and 0 otherwise. So, I look at the product of the two. First, I use the fact that sum of total probabilities has to be 1. So, summation st belonging to Sx, fx st has to be 1, but Sx is same as S1 cross S2. So, this is same as summation st belonging to S1 cross S2, fx st is g1 s, g2 t is 1. Now, here st belongs to S1 S2 is equivalent to saying that s belongs to S1 and t belongs to S2. So, what is happening is I have separated out the terms of s and t in the summation range, and here also. So, that means it becomes a part of this double summation can be written as product of the single summation. So, this same as summation s belonging to S1 g1 s, and then summation t belonging to S2 g2 t is 1. So, fx1 x1 fx2 x2 in this case would be, so this product is 1, you have to remember that, because I am going to the last slide. So, fx1 x1 fx2 x2 is, if x1 belongs to S1 and x2 belongs to S2, then only it would be a non-zero quantity. So, So, it will be a product of this, which is G1 x1, G2 x2, and then summation S belonging to S1 G1 S, summation T belonging to S2 G2 T, and we have seen that the product of this with product of this is 1. So, what you get is joint PMF is same as G1 x1. So, we have since this is total is 1, so this total has to be 1. Fx1 x2, Fx2 x2 is G1 x1 G2 x2, summation S belonging to S1 G1 S, summation T belonging to S2 G2 T. That has to be 1, which implies that Fx1 x1 Fx2 x2 is G1 x1 G2 x2, x1 belongs to S1, x2 belongs to S2, and this is 0 otherwise, which is same as the joint PMF of x1 and x2. So, this implies that x1 and x2 are independent. So, this theorem gives a very easy way to check independence. So, if in the joint PMF sum of in the support, first of all you should be able to separate out the terms of x and y, and in the functional form also you should be able to separate out the terms of x and y. So, let us look at this example. So, z is equal to x y has this PMF y by 55 if x 1 less than or equal to x less than or equal to y less than or equal to 5, 0 otherwise. Find the conditional PMF of x given y is equal to y, where y is fixed at 1 to 5, and y given x equal to x, where x is fixed at 1 to 5. Are x and y independent? Find probability y greater than or equal to 3 given x equal to 2. So, to see this, let us try to see what is the support of x and y. So, x y is a collection of all those st such that st are natural numbers. So, s comma t is n cross n, and 1 less than or equal to s less than or equal to t less than or equal to 5. So, that is what the support of x y is. So, clearly support of y would be what? The second component. If I take s equal to 1, t can go from 1 to 5. So, support is clearly 1 to 5. So, for y belonging to 1 to 5 f x given y, x given y, that is a conditional probability mass function, which is joint probability mass function, probability x equal to x, y is equal to y, divided by marginal of y, which is same as probability y is equal to y. Probability x equal to x, y is equal to y we already have. So, here for fixed x, y can go from x to 5. So, I try to see what is the probability y is equal to y. So, I have to sum out the unwanted variable, which is s over here, probability x equal to s. So, this summation over s says that s y belongs to s x y. But s y belongs to s x y if and only if s and y are natural numbers and 1 less than or equal to s less than or equal to y less than or equal to n. Since y is in s y and this small y is fixed, s can go from 1 to y. So, s equal to 1 to y, and probability x equal to s, y is equal to y in this range is y by 55. So, this turns out to be y square by 55. So, thus for fixed y belonging to 1 to 5, f x given y, x given y is 1 by y if x belongs to 1 to y and 0 otherwise. Now, similarly, if you look at support of x would also be 1 to 5. So, here n was 5. So, for fixed x belonging to 1 to 5, to get the marginal PMF of x, I sum out the unwanted variable t over here in S x. So, it is collection of all those t such that x t belongs to S x 5. Now, note that here 1 less than or equal to x less than or equal to t less than or equal to 5. So, I have to sum t for a fixed x. For a fixed x, t can go from x to 5 and your PMF is y by 55 in this range. So, t from x to 5. So, t from x to 5 and y variable is t variable here, t by 55. So, this is same as summation. So, this you can easily check, these are arithmetic series. So, this 6 minus x 5 plus x by 110. So, f of y given x which is this turns out to be 2y upon 6 minus x upon 5 plus x if y belongs to x, x plus 1 to 5, 0 otherwise. Because you have to see what is the support of y for fixed x. So, s y x. Note that for a range is this. For a fixed x, when x has been fixed at small x, y can go from x to 5. So, y goes from x, x plus 1 to 5, 0 otherwise. Now, to check whether they are independent or not, if they were independent, this conditional probability mass function of y given x should have been independent of this small x, but that is not is happening over here. So, since f x y x given y, I have taken the other probability mass function, but here also one can see that this probability mass function is not independent of this small x. So, they are not independent. And similarly, we have seen before that f x given y x given y, which is over here, if they were independent, this conditional probability mass function should have been independent of this y, which is not happening, because if they were independent, this should have been same as f x x. So, that means this should not have depended on y, because it is only a function of x, but what we have seen, it is depending on y. So, I can immediately conclude that x and y are not independent. So, whether you look at conditional probability mass function of x given y or y given x. One can also check could have directly observed non-independence of x and y from this, because your joint support x and y cannot be separated out, and that is what we are saying, because S x is 1 to 5, S y is 1 to 5, which is not same as S x y. So, that is what I think. Also note that S x is 1 to 5, which is same as S y, and what was your S x y? S x y is correction of all those x y, says that 1 less than equal to x less than equal to y less than equal to 5. X y belong to set of natural numbers. So, because S x y forces x less than equal to y, whereas S x cross S y does not force x less than equal to y. So, that is why the two are not equivalent. So, S x y, which is same as this is not same as S x cross S y, because here S less than equal to t is being forced in this, because it is a cross product, S less than equal to t is not being forced. So, now let us consider the conditional probability mass function of y x given x equal to 2. So, that we have already found for any x belonging to, let us see what we have to find. We have to find the conditional probability mass function of y given x. So, x has been fixed. So, when x is 2, conditional probability mass function of y given x is given by this, whatever x is. So, here x has to be fixed in S x, that means x has to be 1 to 5. So, x has been fixed at 2. So, I get that expression from here, f y given x when x has been fixed at 2. So, that means y would go from 2, 3, 4, 5, and probability mass function would be 2 y, 6 minus 2 is 4, 5 plus 2 is 7, 4 into 7, 18, 2, so 1 by 4, so y by 14, if x is 2, 3, 4, 5, and that is what is over here. So, I have to find out what is the probability that y greater than or equal to 3 given x equal to 2. So, that means I have to find what is the probability y greater than or equal to 2 in this probability mass function. Sorry, y greater than or equal to 3, that is what I had to find in part C. But here in this conditional probability mass function, y takes only value 2, 3, 4, 5. So, this would be same as 1 minus y greater than or equal to 3 would be same as 1 minus probability y is equal to 2, because I am using the same probability mass function. So, it is a given x equal to 2. So, 1 minus probability y is equal to 2 given x equal to 2 is nothing but 2 by 14, which is 1 by 7, which is nothing but 6 by 7. So, let me give this as a take home problem. So, suppose x1, x2, x3 be a discrete random variable with joint probability mass function as given by this, where c is a fixed real constant. So, find the value of c, support of x and support of xi. Now, note that here support of x1 is 1 2, support of x2 is 1 2 3, support of x3 is 1 3. So, here in the joint probability mass function also you can separate out the terms of x1, x2, x3. In the range also you can separate out the terms of x1, x2, x3. So, here one can just through observation say that x1, x2, x3 are independent. So, find the marginal probability mass function of xi. So, for example, to get the marginal probability mass function of x1, you have to integrate out the unwanted variables x2 and x3. Find the marginal probability mass function of x1 and x3, which can be obtained by summing out the unwanted variable x2 over here. then find probability x1 is equal to x2 is equal to x3. So, you have to sum this probability mass function over this range x1 is equal to x2 is equal to x3 to get this probability. Similarly, find the conditional probability function of x1 given x2 x3 is equal to 2 1. Once you have observed that x1 x2 x3 are independent, then conditional probability mass function of x1 given x2 x3 is equal to 2 1 would be same as the marginal probability mass function of x1, the unconditional probability mass function of x1. Find the conditional probability mass function of x1 x3 given x2 is equal to 3. Again, by the same logic, this would be same as the joint probability mass function of x1 and x3. Given x2 is equal to 3, are x1 and x3 are independent? They would be independent because x1 and x2 x3 are independent. So, whether x2 is given or not, x1 and x3 would always be independent. Are x1, x2, x3 independent variables? That we have seen through observations. Are x1 and x3 independent? If x1, x2, x3 are independent, any subset of them would be independent. So, x1 and x3 would also be independent. So, I have essentially solved a lot of these parts for you, but still I would say take this as an exercise. Before I end, let me give the abstract of next module. In the next module, we will introduce continuous and absolutely continuous random vectors and study properties of their probability distributions. So, this was all for this module. Thank you for your patience.